Recent events have rekindled interest in the vast expanse of our solar system. For a long time, it was believed that its structure had been fully studied, with only details left for scientists to clarify. But is everything really that obvious? Some data suggest that we may have overlooked something important over years of observation. New hypotheses about possible objects on the periphery of the solar system continue to intrigue researchers. Attention is being drawn to phenomena that do not fit into conventional models. Is it possible that somewhere out there, in the distant cold space, something entirely unexpected is lurking? The year 2024 has seen significant breakthroughs in certain areas of science. But how much do these discoveries have the potential to change our understanding of the universe? And what else is waiting to be discovered? The latest breakthroughs suggest we may have only scratched the surface. Liking this video helps us share these discoveries with more curious minds, and subscribing ensures you'll never miss a chance to explore the universe's secrets alongside us. Let's journey through the stars together. The solar system is a planetary system that includes the central star, the Sun, and all natural celestial objects orbiting it. It formed about 4.57 billion years ago through the gravitational collapse of a gas and dust cloud. The solar system officially recognizes 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. However, in recent years, astronomers have proposed a hypothesis about the existence of a 9th planet, unofficially referred to as Planet 9, which might be lurking at the farthest reaches of our cosmic neighborhood. This is not Pluto, which was demoted from planet status to dwarf planet in 2006. From its discovery in 1930 until 2006, Pluto was considered the 9th planet in the solar system. The first astronomer to propose the existence of a trans-Neptunian population was Frederick Leonard. On August 24, 2006, the International Astronomical Union, IAU, defined the term planet for the first time. Pluto did not fit this definition, and the IAU classified it as a dwarf planet. Scientists believe that Planet 9 is a gas or ice giant located billions of miles from the other planets. It's very hard to explain the solar system without Planet 9, but it's impossible to be 100% sure of its existence until you see it, said Mike Brown. The idea of a 9th planet first emerged after the discovery of Uranus in 1781 by English astronomer William Herschel, and Neptune on September 24, 1846 by J. Gall and his assistant d'Arrest, which proved that the solar system is much larger than previously thought, and that other worlds may still be waiting to be discovered. If it exists, its discovery would be the most significant finding in the solar system in a century, and would help better understand the origin and evolution of giant planets both in our system and in other star systems. Over the past 20 years, a complex orbital structure has been discovered on the outskirts of the solar system. These belong to cold objects from the Kuiper belt, a region of the solar system extending from Neptune's orbit to about 55 AU from the Sun, that orbit beyond Neptune. The Kuiper belt primarily consists of small bodies, the material left over after the formation of the solar system. The objects are mainly composed of volatile substances, known as ices, such as methane, ammonia, and water. At least 4 dwarf planets are located in this region of near space. Pluto, discovered on February 18, 1930, the largest known dwarf planet in the solar system. Haumea, discovered on July 29, 2005. Makemake, discovered on March 31, 2005. And Eris, discovered on January 5, 2005, the second largest after Pluto, the most massive, and the farthest dwarf planet from the Sun in the solar system. Moreover, it is believed that some of the moons of the solar system's planets, such as Triton, Neptune's largest moon, discovered by English astronomer William Lassell on October 10, 1846, and Saturn's moon Phoebe, the most massive of Saturn's distant irregular moons, discovered by W. Pickering in 1899, also originated in this region. Celestial mechanics are well studied enough to confidently assert that the appearance of these orbits cannot be explained solely by the influence of the 8 known planets. The gravitational forces and interactions created by the known objects in the solar system are incapable of forming such a complex and stable architecture of orbits. This fact points to the presence of an unknown source of gravitational influence that could explain the observed anomalies. Such a source might be a hypothetical new planet located on the outskirts of the solar system, whose gravitational influence forms these unusual orbits. If confirmed, its existence would significantly expand our understanding of the structure and dynamics of the solar system. Technically, the mystery of the ninth planet began in 1992, when the first trans-Neptunian bodies were discovered, objects orbiting our star at a distance greater than Neptune's orbit. This discovery sparked a debate regarding Pluto, and led scientists to conclude that it was merely the first discovered object in the Kuiper belt. A few years later, after thoroughly studying the orbits of these objects, a strange pattern became evident. The motion of such bodies could no longer be explained by the gravitational influence of Neptune or other planets in the solar system. All the calculations led to the conclusion that the hypothesis of a ninth planet in the solar system should be reconsidered. The first proposal from astrophysicists regarding a new planet came in 2002. The sharp decrease in the number of Kuiper belt objects was attributed to the influence of a planet the size of Mars located at 60 astronomical units. However, it turned out that the calculations did not match the observations. Similar unsuccessful hypotheses emerged in 2008 to explain more subtle properties of the Kuiper belt. Other ideas were proposed after the discovery of more distant objects loosely associated with Neptune, such as 2000 CR 105. Its orbit could have been explained by an interaction with a new planet, but it turned out that it could be fully explained by the influence of known planets. On the other hand, the orbit of Sedna, whose perihelion, the closest point to the Sun, is 76 astronomical units, can indeed only be explained by an external influence, either by a planet or by nearby stars. However, in a 2006 study, numerical modeling showed that the orbits of 2000 CR 105 and Sedna could be explained by a planet with a mass between Neptune and Jupiter, located at a distance of 100 to 1000 astronomical units. An independent hypothesis was put forward in 2014 after the discovery of a new small body, 2012 VP 113, far beyond the sphere of influence of the planets. Astronomers noticed that the perihelion of objects beyond 150 astronomical units is clustered in a small area of space. Astronomers suggested that a planet with a mass several times that of Earth could maintain such a grouping through the Kozai-Lidov resonance. A body with a mass of 5 Earth masses in an orbit with a radius of 210 astronomical units could stabilize the orbit of 2012 VP 113. But it was not possible to explain the stabilization of other similar objects' orbits using the same mechanism. Ultimately, it turned out that the explanation using the Kozai-Lidov resonance requires the simultaneous existence of several planets. In 2017, it was discovered that the plane of the belt within 50 to 80 astronomical units is unusually tilted relative to the solar system. A Mars-sized object on a highly inclined orbit was proposed. Such an orbit is theoretically possible, but the object would be brighter than 17th magnitude. So over 170 years, several planets beyond Neptune have been proposed, but all these hypotheses rely on selective data analysis. The evidence supporting the hypothesis of the existence of a ninth planet is primarily related to the unusual orbits of several trans-Neptunian objects, TNOs, which cannot be explained solely by the gravitational influence of the known planets in the solar system. One such object is Sedna, which was discovered on November 14, 2003, by American astronomers Brown, Trujillo, and Rabinowitz. Sedna attracted the attention of astronomers with its unusual orbit, characterized by an extremely large aphelion and perihelion. Sedna's perihelion is 2.5 times farther from the Sun than Neptune's orbit, and most of its orbit lies even farther away. The aphelion is approximately 960 AU, which is 32 times the distance from the Sun to Neptune. Sedna's orbit has a period of about 11,400 years, making it one of the most elongated among known objects in the solar system. Such an orbit cannot be explained by the gravitational influence of Neptune or other known planets. These features have led scientists to consider the existence of a massive object in the solar system that could be influencing the orbits of objects like Sedna. Other examples of unusual TNOs include objects such as 2012 VP-113, 2004 VN-112, 2007 TG-422, 2015 TG-387, and 2004 XR-190. 2012 VP-113, also known as Biden, was initially discovered on November 5, 2012, in one of the images taken with the dark energy camera mounted on the 4-meter Victor Blanco telescope at the Cerro Tololo Inter-American Observatory. Subsequent observations confirmed that this is a large, previously unstudied object, whose orbit reaches a maximum distance of 452 AU from the Sun. To study the orbit and surface of 2012 VP-113, the 6.5-meter Magellan telescope of the Carnegie Institution in the Las Campanas Observatory, Chile, was used. 2004 VN-112 was discovered on November 6, 2004, during observations at the Cerro Tololo Observatory, and it is, on average, located more than 300 AU from the Sun. Upon discovery, the object was designated 2004 VN-112, later assigned number 474640, 2004 VN-112, and then it was named after the Alicanto bird. This is a giant bird from Chilean miners' mythology, with metallic-colored wings, a powerful hooked beak, and predatory claws. The orbit of 2004 VN-112 is characterized by high eccentricity, 0.850, a moderate inclination, 25.58 degrees, and a semi-major axis of about 316 AU. As of January 11, 2017, the orbit was calculated based on 34 observations over a 5,821-day observation arc and has an absolute magnitude of 6.5. The object was subsequently found in sky images starting from September 26, 2000. Michael Brown's website lists this object as a minor planet with a diameter of approximately 314 kilometers. The visible spectrum of 474640, Alicanto, differs from Sedna's spectrum. The slope of the spectrum suggests that the object's surface may contain pure methane ice and amorphous silicates. 2007 TG-422 is a scattered disk object discovered on October 3, 2007, at the Apache Point Observatory. 2007 TG-422 passed perihelion in 2005 at a distance of 35.5 AU from the Sun. Until 2018, the object was visible in the constellation Taurus, and its opposition was observed on November 29, 2017. The orbital parameters of 2007 TG-422 vary depending on the epoch. In 2007, its orbital period was estimated at 10,611 years, with an aphelion distance of 930 AU, but by 2012, these parameters had changed. The period increased to 13,512 years, and the aphelion distance to 1,099 AU. Due to the high eccentricity of its orbit, barycentric coordinates for such objects are more stable than heliocentric ones. According to the JPL Horizons Ephemeris system, as of May 14, 2018, the barycentric orbital parameters of 2007 TG-422 are as follows. The semi-major axis is 503 AU, and the orbital period is about 11,300 years. For comparison, Sedna has a larger semi-major axis and orbital period. 2007 TG-422 has been observed 98 times over 7 years and has an uncertainty parameter U = 2. The object has not been observed since 2015. 2015 TG-387, Leleaku Honua, is a trans-Neptunian object in the outer solar system, a sednoid. It was previously known by the nickname Goblin. It is the third known object after Sedna and 2012 VP-113. It was first observed on October 13, 2015 by astronomers David Tholen, Scott Shepard, and Chad Trujillo using the Subaru telescope at the Mauna Kea Observatory. The object's diameter is 300 kilometers. At the time of the announcement of its discovery on October 1, 2018, the observation arc was 949 days. In perihelion, 2015, TG-387 approaches the Sun, at a distance of about 65 astronomical units. Only Sedna and 2012 VP113 have more distant perihelia, with the closest perihelion passage expected in 2078. In aphelion, it is about 2,000 astronomical units from the Sun, while other data suggests it is 2,300 AU away. The orbital period around the Sun is 39,100 years. The orbit of 2015 TG 387 is consistent with the hypothesis of a ninth planet. 2004 XR 190 is a detached trans-Neptunian object, a candidate for a dwarf planet, located in the scattered disk. Astronomers led by Lynn Jones from the University of British Columbia discovered it as part of the Canadian-French CFEPS program using a telescope in Hawaii, CFHT. The discovery team temporarily nicknamed the object Buffy, after Buffy the Vampire Slayer from TV shows. According to the discoverer Lynn Ellen Jones, the object could kill the existing theory of the origin of the solar system, just as Buffy kills vampires. The detached trans-Neptunian object 2004 XR 190 is quite unusual for two reasons. Its orbital inclination is 47 degrees. Such an inclined orbit means the object moves around the Sun, traveling up and down rather than left to right when viewed edge-on along the ecliptic. Secondly, the object has an unusually close to circular orbit for a scattered disk object. While the hypothesis has been proposed that scattered disk objects were ejected into their current orbits due to Neptune's gravitational influence, with significant perihelion distances, it is difficult to reconcile all these orbital configurations with the laws of celestial mechanics. This has led to some uncertainty in existing theoretical models of the outer solar system. How might new discoveries in the outer solar system confirm or alter the hypothesis of a ninth planet? Recent research conducted by Konstantin Batygin, 1986, an American astrophysicist, and Michael Brown, 1965, a professor of planetary astronomy at the California Institute of Technology, has significantly contributed to the development of the hypothesis regarding the existence of a ninth planet. As part of these studies, the scientists conducted a series of computer simulations aimed at determining the possible parameters of the hypothetical planet, based on the observed characteristics of the orbits of trans-Neptunian objects, TNOs. The results of the simulations provided more precise characteristics of the ninth planet, which had previously been uncertain. One of the key conclusions drawn from these studies was the hypothesis regarding the mass of the ninth planet. According to the models by Batygin and Brown, the hypothetical planet could have a mass 10 times greater than that of Earth. This makes it a significant object, comparable in mass to icy giants such as Uranus and Neptune. This mass also explains its ability to exert substantial gravitational influence on TNOs, affecting their orbits and causing the observed anomalies. Furthermore, the simulations allowed the scientists to refine the orbital parameters of the ninth planet. It is estimated that its orbit would be highly elongated with an eccentricity, elongation, that greatly exceeds the eccentricity of the orbits of the other planets in the solar system. The orbit of the ninth planet, according to the models, lies at a distance of 400 to 800 astronomical units, AU, from the Sun. Due to these orbital parameters, the planet could be moving along an orbit that is highly inclined relative to the plane of the ecliptic, the plane in which the other planets of the solar system orbit, which also explains its long presence in distant regions where its light is too faint to be detected from Earth. The models also suggest that a complete orbit of the ninth planet around the Sun could take 15,000 years, which explains why it has not been observed for millennia. Recent studies have also suggested that the orbit of the ninth planet may be the cause of the grouping of the orbits of certain TNOs. Objects such as Sedna, 2012 VP113, and others exhibit unusual orbital characteristics that cannot be explained solely by the influence of the known planets. The computer models by Batygin and Brown indicate that the presence of a massive planet on the periphery of the solar system could explain these anomalies, including the group of TNOs with elongated orbits and their orientation in space. The hypothesis of the existence of a ninth planet, proposed by Konstantin Batygin and Mike Brown, has led to intense debates and a surge in scientific research. The scientific community's reaction to this hypothesis has been diverse, though predominantly positive, albeit with a certain degree of skepticism. On one hand, many astronomers have been inspired by the new opportunities to explore distant regions of the solar system, leading to a series of new observational programs and theoretical studies. On the other hand, the existence of the ninth planet remains unconfirmed, which raises doubts and requires more convincing evidence. Immediately following the publication of the hypothesis in 2016, the scientific community split into several camps. Some scientists saw the proposal as a logical explanation for the observed anomalies in the motion of trans-Neptunian objects, TNOs. These anomalies, including the clustering of TNO orbits, could not be explained solely by the influence of known planets. The ninth planet hypothesis offered a potential solution to this mystery and a new perspective on the dynamics of the outer solar system. Other scientists approached the hypothesis with caution. They pointed out that the observed orbital anomalies might result from other processes, such as interactions with the galactic tide, mass distribution in the Kuiper belt, or even errors in observational data. In response to these arguments, additional studies were conducted to refine and verify the data, ultimately leading to a deeper understanding of TNO dynamics and the potential existence of large planetary bodies at the solar system's periphery. The statistical confidence in the existence of the ninth planet, achieved by scientists based on the latest models, stands as one of the most compelling arguments in favor of this hypothesis. The 5 sigma level of statistical significance, derived from the analysis of the orbital data of trans-Neptunian objects, TNOs, virtually rules out the possibility that the observed anomalies in their movement could be random. For comparison, this level of significance is used in physics to confirm the discovery of new elementary particles, such as the Higgs boson. 5 sigma means that the probability of error or coincidence is 1 in 3.5 million, making the ninth planet hypothesis statistically highly credible. This result was obtained through a meticulous analysis of the orbits of 13 trans-Neptunian objects, whose parameters show a clear clustering in space that cannot be explained by the influence of known planets. The models developed by Batygin and Brown account for all possible factors that could affect these orbits, and conclude that the only plausible explanation is the presence of a massive celestial body on the periphery of the solar system. However, despite such high statistical confidence, the question of the ninth planet's existence remains open. Could it be that our understanding of gravitational interactions within the solar system is still incomplete, and that there are other factors capable of explaining the observed anomalies? Or is there indeed another planet lurking at the edge of the solar system, whose existence challenges current conceptions of the structure of our planetary system? It is worth noting that the 5 sigma level of statistical significance was first used in astrophysics in 2012 to confirm the existence of a new elementary particle, the Higgs boson. This discovery was a revolutionary event in physics and led to the revision of many theoretical models. The application of such a stringent criterion in the case of the ninth planet shows how seriously scientists take this hypothesis and how convincing the modeling results appear. Nevertheless, in astronomy, as in other sciences, not only statistical analysis, but also direct observation is crucial. Without actual observation of the ninth planet, its existence remains a hypothesis, albeit a highly probable one. If the ninth planet indeed exists, what other surprises might it hold? What will its physical characteristics be? And could there be something even more mysterious hidden beyond its orbit? With each new step in the search for this planet, scientists come closer to answers. But is there something still eluding our attention? Models based on the hypothesis of the existence of a ninth planet indicate its significant influence on the dynamics of objects in the distant regions of the solar system. One of the most intriguing features of these models is the ninth planet's ability to explain the clustering of orbits of certain trans-Neptunian objects, TNOs. The clustering observed in the orbits of such objects as Sedna, 2012 VP 113, and others, lies in the fact that their perihelia, points of closest approach to the Sun, are grouped in one direction, which should not occur randomly. Under the influence of only the known planets, such as Neptune, these objects should have gradually scattered along their orbits, losing such a clear orientation in space. However, the presence of a ninth planet with its massive gravitational field could maintain the TNOs in these orbital configurations. It is also hypothesized that the influence of the ninth planet extends far beyond the Kuiper belt, affecting objects located hundreds of astronomical units away from the Sun. The gravitational pull of this planet could stabilize the orbits of such objects, preventing their disruption or ejection from the solar system due to interactions with Neptune or other gas giants. An important aspect of this influence is the ninth planet's ability to counteract gravitational perturbations from Neptune. In the absence of the ninth planet, TNOs with elongated orbits would experience strong perturbations, especially if their orbits intersect with Neptune's. However, models suggest that the ninth planet could act as a stabilizer, preventing such perturbations and ensuring the long-term stability of the TNO's orbits. This explains why objects like Sedna and 2012 VP-113 remain on their unusual orbits despite potential gravitational influences from other planets. The large-scale influence of the ninth planet could also explain the presence and behavior of other small bodies in the distant regions of the solar system. For instance, it might be responsible for the formation of groups of objects with specific orbital inclinations, or for the existence of objects with extremely elongated orbits, which cannot be explained within the framework of current models without considering its gravitational impact. If its influence is indeed so substantial, could there be something even more significant behind it? What other undiscovered forces might be at work on the fringes of our planetary system?